Welcome to video lecture O, or maybe 0 if you like. It's the very first one. This is an overview of linear algebra. My goal in this is to give you some sense of a map of the whole terrain that we're about to cover here. Some things won't make sense. They'll be a little bit vague because I can't make them all precise in a reasonable amount of time. That's what the course is for. But I'm hoping that you'll be able to come back to this maybe at the middle of the course or the end of the course, maybe before the summative exams, and see how much more sense these things make. With all video lectures, I recommend you can speed it up or slow it down depending on how quickly you can absorb the things I say or the things that I see on the slide, and you can always go back and just review certain portions of it, and I highly recommend that strategy. I mean, these are a tool to help your learning. You don't need to view them as a piece of art like a movie to be viewed in a certain way. Linear algebra sits at the crossroads of mathematics, science, engineering. It's ubiquitous. Pretty much all mathematicians need it. Not all mathematicians use calculus in their everyday existence, but linear algebra is so common that pretty much all mathematicians end up using it, and applied, it's all over applications in engineering and other mathematically based disciplines, statistics in particular. And it's a beautiful subject. It's a rich interplay of algebraic, geometrical, and analytical thinking. And by the end of the course, I hope that you'll be able to look at the same phenomenon, often from different points of view, each of which sheds its own light on the topic. Okay, so where does linear algebra come from? Well, its origins are in solving systems of linear equations. So going back to high school or maybe elementary school, you know how to solve one equation and one unknown, and then you generalize that and you can solve like two equations and two unknowns, and you know how to do that by elimination or whatever. We're not there yet, but the important thing to understand is that you can take a system of equations like this and convert it into an equivalent matrix vector equation. So this is a matrix that just has those coefficients 2, 3, 4, 7, and then you've got the vector xy that equals 4, 6, and multiplying this times this is exactly, and saying it equals that gives exactly the same information as those equations. But when you encapsulate something into a single entity, it becomes easier to deal with, and that's just a common theme in mathematics. The other important thing to be thinking about is that a matrix will represent a special kind of function from r to the n to r to the m. What it represents, in fact, is a function which is linear. So you've already seen some multivariable calculus, probably, and here these are the multivariable functions that are exactly linear. I mean, they're linear in the sense that they have to map 0 to 0. So they're lines through the origin if we were just in single variable calculus. And in calculus, the main goal was to study more complex functions using simpler functions, linear functions, which are straight lines or planes or whatever, tangent planes. And so that's what this kind of a matrix does, is it gives you the main part of the tangent plane to more complicated functions. And you may have seen the Jacobian matrix of partial derivatives if you've had multivariable calculus already. Outside of calculus, many situations deal with vectors of values. So this is a separate theme from the calculus theme, but there's vectors of values that you want to understand. Like you could have, take snapshots of some image at a bunch of different wavelengths and make a vector of the darkness in that particular location, that kind of pixel. And you could say, okay, so I've got a whole vector associated with a bunch of different points. How do I understand what's really going on? What weighted combination of those values gives me the best read on something? That's roughly the idea of things you're trying to look at. Or big data, the goal of people who run things like Google and Facebook and whatever is to understand you. So they might have a vector associated with each person that browses that says something about their past browsing history, whether they're likely to buy things, where their political leanings are. There are all kinds of things that they can keep track of. And then by analyzing a bunch of the data, they can say, well, what are the trends? People like this, are they likely to go out and spend a lot of money on this website or not? And so then they know how to treat you as you arrive at that website. So linear algebra has ways of revealing patterns that are otherwise invisible when you're just looking at lots and lots of numbers in vectors or matrices. In order to take advantage of the power of mathematics, really, it's important to be able to go back and forth, to be flexible in your thinking between concrete and abstract points of view. So will want to use both points of view to understand linear transformations, both as concrete matrices or as concrete matrices that can be written with respect to, say, a different coordinate system. This idea of having flexibility in your choice of coordinate system is kind of like, do you want to use rectangular gridded coordinates, like this? Or do you want to have more polar coordinates? Is that more natural? Are you living in Amsterdam, where polar coordinates are a more natural way to think about the world? And in 3 dimensions, you've also probably seen spherical and cylindrical coordinates. So sometimes that's a better way to understand things. So this idea on steroids is at the core of a lot of linear algebra, where we're trying to change the coordinate system with which we understand vectors, the way we actually write a vector down. We change the coordinates in which we write it, and that changes the matrices that act on it in a way that the matrix can be easier to understand. Now, if you think about it, a matrix, even that 2 by 2 matrix had 4 entries. And if you've got like a 5 by 5 matrix, that's 25 entries. It's growing like n squared, which is pretty fast. Often we can understand, with the right coordinate system, we can understand a matrix almost completely, as well as we need to, just using its n eigenvalues. If we've got a non-square matrix, then we might use its singular values instead. And that'll tell us the things that we care about. So this kind of analysis of a matrix is really important. A lot of this analysis can be framed in terms of factoring a matrix into more easily understood pieces. It's like saying, instead of having one transformation that does this complicated thing, we'll split it up as a sequence of transformations that do simpler things. So row reduction that I mentioned here is the same thing as an LU decomposition. It's a way of splitting up a matrix as a lower triangular one and an upper triangular one, which makes it easy to, say, solve a corresponding system of linear equations. Diagonalization is a way of changing coordinates in such a way that you get a diagonal action of a matrix, which is very easy to understand because it just stretches certain directions proportionately but keeps them pointing in the same direction. Graham-Schmidt split these things up as an orthogonal matrix times an upper triangular, and the SVD, arguably the most useful thing that people use in applications, splits a matrix up as some kind of rotation, basically an orthogonal matrix, followed by something that's basically a diagonal matrix, block diagonal matrix, but rectangular, and then another matrix which is also just a rotation or maybe a reflection, an orthogonal matrix. And so that makes it much easier to understand than if all we have is the original matrix with its n squared entries. The video lectures will be organized not according strictly to Lay's textbook, which may not be the only textbook that people viewing these video lectures will follow going forward. So I'm giving things labels here, so you can see I've got A, B, C, not C, A, B, D, E, F, G. So A is for applications, B is for bases and subspaces, D is for determinants, E is for equations, F is for factorization and decompositions, G is for geometry, M is for matrices and linear transformations. The path of the course will be starting with the equations section, we'll move into matrices and linear transformations, understanding these transformations that I've been telling you about. Determinants are a simple tool. That'll just be a quick sideline to a useful computational tool, but we need it in order to talk about the eigenvalues that come up later on. First, we'll talk about bases and subspaces, so that'll involve a lot of row reduction, the LU decomposition of U will, that are associated with a matrix. And that's sort of the algebra part of linear algebra. And even the first factorization, the diagonalization that we get with eigenvalues, is really something that you can do just with the algebra. But to really harness some of the power of linear algebra in standard spaces, you need to take advantage of geometry. You need to have a product which takes two vectors as input and outputs a scalar. So sometimes called a scalar product or an inner product or a dot product, because you've seen the dot product before perhaps, and that's just what it is in R to the n or C to the n. So we'll talk about geometry, which gets us into the idea of orthogonality. So certain bases that are orthogonal, perpendicular to each other, have useful properties that make them easier to understand than just a general basis. And that'll go along with orthogonal projections. It's a process called Graham-Schmidt, which takes any basis and turns it into an orthogonal or orthonormal one. And then finally, that end of that chapter we'll talk about least squares approximations. And so finally, some of the highlights of the course are in Chapter 7. So we'll find out that we can diagonalize real symmetric matrices always. You can't diagonalize every square matrix, but real symmetric matrices you always can. And that'll lead us through a very nice path to the singular value decomposition. So that's the quick overview for the course. And here are the course learning objectives. So these are the things that I expect and that I hope you'll be able to do, and that it's my goal to help you get. So if you feel like there are parts of this that weren't covered adequately in the course or you wanted more help with, let me know, and I'll see what might be possible in future iterations of the course at the very least. So the first one is that you're going to learn how to perform operations on matrices. Gaussian elimination is another name for row reduction, that elimination of variables that lets you solve equations. Matrix multiplication is not that hard an operation, but taking inverses of matrices can be hard with respect to that multiplication. Computing determinants, there are better and worse ways. There are ways that are good theoretically that aren't so good computationally. We'll talk about all of that. And then I'll, of course, want you to be able to interpret the results in terms of the corresponding linear systems and transformations, because otherwise you can't make any use of this for applications. We'll want to be able to analyze properties of sets of vectors, linear dependence and independence, and talk about vector spaces. So spaces mean that if you add two vectors or multiply by scalar, you stay inside the space. So they're sort of self-contained. And the self-contained ones that are associated with the matrix are the null space, the column space, the row space. And these come up all the times in understanding applications. There's a special way they're related by the rank nullity theorem, which you'll see. And then another chunk of the course will be eigenvalues and eigenvectors, are things you might have even heard already. They're an incredibly powerful tool for understanding how square matrices act. And particularly it's useful when you're iterating a map over and over again that tells you about a certain process that might happen month by month or day by day, hour by hour even. But if it's iterated, then understanding what happens in the long term usually depends heavily on the analysis of its eigenvalues. So those are the first three. There are 8 in total. 4, 5, and 6. So in 4, we're leveraging the geometry, the inner product spaces, as I mentioned earlier. Learning outcome 5 is that I hope you'll be able to, know how to decide whether a matrix has certain factorizations that are useful and be able to compute them, determine optimal coordinate systems to understand situations, and use these to analyze the original situations that you're handed. As applications, you'll be able to compute least squares approximate solutions to linear systems. When there's no actual solution to a set of linear equations, sometimes you can find the best possible fit, because you still need to know how to act, even if you can't find, even if no real solution satisfies all those equations. We'll talk about simplification of quadratic forms, which allows us to do constrained optimization problems with them, kind of thing that comes up all the time in applications. Finally, 2 things that are a little bit more meta level is I'd like you to be able to leverage your geometric intuition and your powers of visual, and what we can do to visualize the low-dimensional examples that we'll be looking at. 2, 3 dimensions are things we can visualize. It's harder. Vectors of length 10 and 12 and hundreds and thousands even come up all the time in current day applications. But in order to make sense of them, you want to be able to leverage what we can visualize in 2 and 3 dimensions. So we'll be doing that throughout the course, trying to leverage geometric intuition and visualization to make sense of all these concepts that are often presented very algebraically. Of course, you'll still often need the precise algebraic definition to prove certain statements. And now here's the thing that maybe for some of you may involve more work than you were expecting, which is getting better at distinguishing true statements from false ones within the theory of vector spaces, linear transformations, and the representations of matrices. There will be lots of true and false questions. Some of them I'll ask you in class just in a way to see how your learning's going. Some of them will be asked on summative assessments like quizzes or exams. Learning how to give a counterexample to a statement that's false, example that shows that some statement is false. It's usually the cleanest way to do it. And learning how to give a simple, a few lines of argumentation that show how you get from point A to point B to show that something is actually true. Those are the goals for the course. You're not expected to be able to do this at the level of math majors yet, but the problem is that you really can't understand the theory and make the most use of it for applications if everything you do is rote memorized learning. And so this is how we get beyond that to higher levels of thinking. And at this point in your mathematical development, if you haven't seen this already, you're certainly ready for it. That's the other big thing that we'll be doing in this class. And that's it. That's the overview of linear algebra. Thanks for your attention. Feel free to come back to this video later. And as always, send me comments if you have things that you think I said too quickly or not clearly enough or anything like that. But also things will become clearer in the later lectures. Thanks. Oh, what happened?